All right, let's talk about the Pythagorean Theorem. I know. You probably remember it from middle school geometry. But what if I told you that simple formula you memorized is hiding a secret history that's 4,000 years old? A story packed with ancient codes, a philosophical crisis that may have led to murder, and, get this, the very definition of space itself. We all know it, right? A squared plus b squared equals c squared. For any triangle with a right angle, the squares of the two short sides add up to the square of the long one. It's simple. It works. But here's the question. Is that formula really the heart of the theorem? Or is it just a modern way of talking about a much deeper, more visual idea? So, here's the first secret we need to uncover. The theorem was never really about algebra in the first place. Its true identity is all about geometry. It's about physical, tangible areas you can actually see. This is how the ancients really thought about it. See, before algebra was a thing, squaring a number wasn't just a calculation. It meant you literally drew a square on that side of the triangle. The theorem was a physical truth. You could take the two smaller squares, maybe cut them up, and they would perfectly, exactly fill the area of the bigger one. No algebra needed. You know, one of the most beautiful proofs of this, often credited to the Indian mathematician Bhaskara, doesn't use a single number. It's just a picture. You start with 4 identical right triangles. You arrange them, just like this, and their longest sides, the hypotenuses, form a new tilted square right in the middle. The area of that empty space in the center, well, that's c squared. And now for the magic trick. You take those exact same 4 triangles inside the exact same big square, and you just slide them into the corners. And look at that. The empty space has changed shape. It's now 2 smaller squares. One has an area of a squared, and the other b squared. Now think about it. The big box didn't change, the triangles didn't change, so the empty space has to be the same amount in both pictures, which means c squared times must equal a squared plus b squared. The legend says Bhaskara wrote just one word next to this diagram. Behold. I mean, what else do you need to say? And that brings us to the second, and maybe the biggest, secret of them all. The guy the theorem is named after, Pythagoras, he didn't discover it. Not even close. In fact, people were using this as a practical tool more than 1,000 years before he was even born. Just look at this timeline. We have clay tablets from ancient Babylon dating back to 1800 BCE that not only use the theorem but list out whole sets of numbers that perfectly fit the formula, what we call Pythagorean triples. Pythagoras was born around 570 BCE. That's a 1,200-year gap. This wasn't some abstract Greek philosophy to start with. It was a practical rule for builders and scribes in Mesopotamia. And the star witness in this whole story is this little clay tablet, Plimpton 322. It looks unassuming, but etched into it are 15 rows of numbers that form incredibly complex Pythagorean triples. We're talking numbers like 1191, 120, and 169. You don't just guess those. The Babylonians clearly had a system, a method. But what on earth for? Well, this has sparked a massive debate among historians. On one side, you have scholars like Eleanor Robson, who think it was basically a teacher's cheat sheet, a list of nice numbers that would give clean answers for math students. Kind of a practical, if a little boring, idea. But then you have this other, far more radical theory from a couple of mathematicians, Mansfield and Wildberger. They argue this is the world's very first trigonometric table, used by ancient surveyors to build temples and canals with perfectly calculated slopes, a full 1,500 years before trigonometry was supposedly invented. So when this practical builder's rule finally gets to ancient Greece, it's completely transformed. It stops being just a tool and becomes a philosophical cornerstone, one that would eventually trigger a massive intellectual crisis. You see, for Pythagoras and his followers, who are kind of like a secretive math cult, the universe wasn't random. It was a beautiful, ordered cosmos, and the rules that governed it were whole numbers and their simple ratios. They saw these ratios everywhere, in the harmonies of music, in the movement of the planets, and the theorem, for them, it was the ultimate proof that the universe was rational and knowable. But their obsession with pure logic ended up setting a trap for them. They asked a fatally simple question. What happens with the most basic right triangle you can possibly imagine? One where the two short sides are both length 1. Well, 1 squared plus 1 squared is 2, so the long side, the hypotenuse, must be the square root of 2. And right there, Their entire worldview started to crack. The problem was they tried, and they could not find any simple fraction, any ratio of two whole numbers that would equal the square root of 2. And that's because it's impossible. We call this an irrational number. But for the Pythagoreans, this was a logical scandal. They called these numbers alogon, which means unutterable, because they represented a flaw in their perfect universe, a truth their philosophy just couldn't handle. And, ironically, they used their favorite weapon, pure logic, to prove this horrible truth to themselves. It's a beautiful proof by contradiction. First, you just assume for a second that the square root of 2 can be written as a fraction, and that it's in its simplest form, let's say m over n. Okay? Well, if you follow the logic from that one assumption, you can prove that both m and n have to be even numbers. But wait, if they're both even, then the fraction wasn't in its simplest form to begin with. You just contradicted yourself. That means the only thing that could possibly be wrong was your very first assumption. Boom, the square root of 2 cannot be a fraction. Game over. And if you want to know how serious this crisis was, just look at the legend of Hippasus. The story goes that he was the Pythagorean who first discovered this terrible secret. And for daring to reveal this flaw in the universe to the outside world, his brothers took him out on a boat and drowned him. His crime was basically heresy against their religion of numbers. Okay, let's jump way forward in time, about 2,000 years. After all that philosophical drama, the theorem gets a massive upgrade and finds its ultimate modern form, all thanks to the 17th century thinker René Descartes. What Descartes gave us was the coordinate grid, the XY plane, and this allowed the theorem to be reborn as the universal formula for distance. Think about it. Any straight line between 2 points on a grid can be seen as the hypotenuse of a right triangle. The other two sides? They're just the change in x and the change in y. All of a sudden, that ancient geometric rule became the engine for calculating the distance between any 2 points. And the real power of putting it in this algebraic form is that it's infinitely expandable. Want to find the distance between 2 points in 3D space? No problem, just add a z-squared term. Working in 4 dimensions, or 10? Just keep adding terms. The theorem becomes the fundamental ruler for measuring any space, no matter how many dimensions you can dream up. And this brings us to our final secret. And honestly, this one is the most mind-bending of all. It turns out the theorem doesn't just work inside a certain kind of space. The very fact that it works at all is what defines that space. Think about it this way. On a flat piece of paper, what mathematicians call a Euclidean plane, a squared plus b squared will always equal c squared. But what happens if you try to draw a big right triangle on the surface of a globe? All of a sudden, the formula breaks. A squared plus b squared no longer equals c squared. The theorem's truth is the ultimate litmus test for flatness. Its validity is what defines the absence of curvature in space itself. Which leaves us with one last pretty wild thought. This ancient principle is the very definition of flat space. But we now know, thanks to Einstein, that we don't live in a flat universe. We live in a universe where massive objects like stars and planets actually bend and curve the fabric of space-time. So what happens to the most famous theorem in history in a universe like ours? It means its incredible 4,000-year journey, from a builder's rule on a clay tablet to a description of the cosmos, well, it's still not over.